Hello students, today we are going to move to the new chapter name is process synchronization, and this is our lecture number 12. And under this topic today we will discuss few important things with respect to process synchronization, why we need process synchronization. So we are going to basically cover through this lecture the meaning of data inconsistency and race conditions, and we are going to cover the critical section problem and the solution to the critical section problem. So we'll move ahead. So before I go about directly jump into the this technical terms, let me give you a brief overview. Okay, suppose there is a process. Suppose there is a process. Okay, suppose there is a process. This is a process P1, and there is another process P2. Now when any process is there, okay, whenever such kind of process, whenever those things are in the secondary storage device and has to be executed, so you want to execute this process P1 and P2, or we program P1 and P2. Now it has to be first brought into the RAM. This is my RAM, okay, in other words primary memory. So whenever any program or any process has to be executed, it has to be first brought into the RAM. So say for example I have brought this or the long-term scheduler, I have imported process P1 and process P2 in the RAM. Okay, so in one part of the RAM is always reserved for this OS. Okay, but the remaining section of the RAM is used for executing the user program, and I want to execute this process P1 and P2. So process P1 and P2 now imported into this first and second partition. Okay, now these processes are in the RAM. Now during the execution of this process, the CPU will sometimes, suppose this is my CPU, and this CPU will switch from one process to another. Sometimes it will execute some of the instruction of P1, and sometimes it will execute some of the portion of or some code of the P2. So it will flip too frequently between process P1 and P2, assuming that on the RAM or in the main memory there are only two process P1 and P2 for which CPU has to do the execution, or has to execute those codes. So during the execution of P1 and P2 which are there in the RAM, CPU will keep on frequently move from here to here, from P1 to P2 or from P2 to P1. When process P1 will go to the process P1 tries to perform IO bound jobs, then it will switch over to P2, and whenever P2 will perform IO bound job, then it will switch over to P1. So like that way CPU is always busy throughout the time, okay, for executing this code of or the instruction that is stored in the written in the memory. Okay, so now during this execution it may happen that some portion, okay, some portion of the memory, okay, some portion of the memory held by this process P1 are shared. Okay, suppose this is the portion of memory which may contain some data, or which may contain some variable or code, whatever may be the scenario. Some portion, some logical portion is being shared by this process P1 and P2 and are executing concurrently or parallelly one after another. Okay, so in that such kind of process which share some logical address space in which some data and instructions are there, such kind of process is known as a concurrent process. So I've just introduced meaning of concurrent process. So basically what kind of process are known as a concurrent process? The process which shares some logical address space during the execution, and that logical address may contain data or instruction or both. So such kind of process is known as a concurrent process. Now when there is a concurrent process, it may be one more than two. Okay, so when there are many concurrent processes that are being executed in the RAM or main memory, then it might happen that the same memory location is being accessed by this both process at the same time, or maybe one after another or at the same time. Okay, so whatever be the scenario, it when it access when it try to access the memory location at the same time, and it leads to a problem of data inconsistency, which will be my next topic, right? So we'll move back to this slide. Suppose I want to introduce basically data inconsistency and the importance of data inconsistency. Okay, so to do that, we need to understand what is the meaning of cooperating process. Right? So cooperating process are the process which share some logical address space, and in that logical address space you have got the data or the code. Now data, you may consider that there is a variable, okay, and that variable is stored in some part of the main memory, and that memory location is being shared by cooperating process. Now for cooperating process, it is not necessary that there is only two process like the one that I've shown you in the example. It might be more than two. So there may be more than two process. There might be more than two process that will be sharing common logical address space, inside which there are some code and data. Now when this is the scenario, then it might happen that during the execution of such type of cooperative process, it might happen that it may get affected. Okay, the code may get affected, or the content of the variable may get affected, or it may affect others also. So say for example, suppose uh, suppose there are list of process P1, okay, and P2 and P3, okay. So there are a list of process and they are cooperating process, CP, okay, they are cooperating process. So these process will share a common memory, okay, although it have got some independent memory location. Say for example, this is an independent memory which is not being shared. For this process P2, this is an independent memory which is not being shared. For this process P3, this is an independent memory which is not being shared, but this memory is being shared to all of them. So it might happen that sometimes P1 will access this, P2 will access this, P3 will access this. So it may lead to problem of data inconsistency, right? So we'll come back to the again slide. So now during the execution of this cooperating process, so it may affect one another. Okay, it may affect one another. So when it tries to affect one another during the execution, then it may lead to a problem, a very very big problem, important problem, known as a data inconsistency problem, right? So we will try to understand this with the help of the example in the next slide. So, but before that, let me give you a scenario from programming aspect, or in programming duration. What could be the scenario of, or what is the scenario, or in what situation data inconsistency may happen, right? Say for example, there is a global variable which is declared as int count, okay, with some value. Say for example, it's 5. So now count int value, okay, count is a integer variable with some value. Say for example, the value is 5. Now you can see this, the green color shaded region code is one code, and this orange color region is the another code. Now both of them is trying to update the value of count. Okay, maybe there is some problem. Okay, so it should be count plus plus and minus minus. Okay, so it should be something similar to this. Yeah. So this green color code is trying to increment the value of the shared variable count, and this is trying to decrement the value of count. Okay, suppose the initial value of count is 5. Now this code will make it 6, whereas this code will make it 5. Okay, so this is an example in the program example where the shared variable is being modified by different functions or different code, right? So I am assuming that this code is there with one function and this code is there with another function, and this count variable is being shared. Okay, so this, having said this scenario, we'll move forward to understand the problem of data inconsistency. So you can see over there that the count plus plus and count minus minus is written in high level language form. If we try to rewrite the same thing in machine level code, so it may be considered as this. For example, suppose you are trying to execute count plus plus, and how this same instruction is being can be written in low level language or machine level language. Okay, so first what we'll do is that whatever is the value of count will get initialized in the register. So all the operations, arithmetic and logical operations, will happen in the register directly, so because it is a memory location, right? So now the content of count memory location will be copied into the register 1. This register is basically it's a general purpose register, GPR. Now, and after that, whatever is the value that resides in the register 1 will get incremented by 1 and will be assigned to register number 1, or basically replaced it. Okay, and then after that the reflection will be made to the memory location with the help of this third statement. So until this third statement is not executed in the memory, the reflection will not be made in the memory. The value is 5. Okay, say for example my initially the count value is 5, so 5 will be initialized to the register 1, and after that the operation is taking place in the register, not the memory location. So here in the second step, the memory is not being updated, rather the register content is being updated by 1, and using the third statement, after completion of third statement, then only the content of the value in the memory will be reflected. Similarly, it will follow for the count minus minus. So I'm not worried about that, whether the increment and decrement is written before or after the variable name. So somehow the other it will decrement, and somehow the other it will increment. Okay, so the first one it will increment, and second it will decrement. Now if I want to represent this second code, count minus minus, how this is interpreted at machine level form is that, initially whatever was the value of the count, say for example it's 5, will be loaded into the register number 2. Then whatever is there in the register number 2, now it's currently it's 5, so it will be decremented by 1, that is 4. So 4 will be initialized to register number 2, and then reflection will be made in the memory only after execution of this count equals to register number 2. So having said this, if we let us go back to this code, so now you can imagine that this count plus plus or count minus minus can be represented in machine level code in 3 different steps. Okay, as shown this and this, right? So now we'll try to understand in more detailed form. We'll try to understand that how this code are executed. Okay, say for example the CPU is trying to update the value of count of both the functions, right? Maybe by executing C++ or C minus minus. So during the execution of C++ and C minus minus, which in turn the actual code is basically these 3 statements and the next 3 statements. When these statements gets executed in interleaving fashion means it might happen that these at time stamp t1, the first instruction of this blue color code is being executed, and at time stamp t2 it might happen that next code that is being executed by CPU is this. So interleave fashion. So you may consider that interleave fashion as something similar to this one. Suppose suppose this is the first code that is being executed by CPU from the green color program. Okay, and this is another code from the red color program, and again this is a green color code from the green color program, and again this is red color. This is an interleaved fashion, so one after another, or it might happen that it is executed in very random way. Here in this case I have shown one after another. Okay, one code from the one program and the code from the other program. So it may happen that 2 code from the one program and 1 code from the other program also. So there are various lot of different kind of scenarios that it can happen. So having said these things, okay, I want to basically update the count variable, and the count variable can be incremented. For incrementing count variable code, actually the machine level code is this 3 statement, and for decrementing actual code is this 3 statement. Now when these statements are executed in interleaved fashion with value count, what will happen? So for example at time first unit of time, so t0 is CPU has executed a particular code at this time. Okay, 0 unit of time, 0 1 2 3. So at one time only one code can be executed. So there are 3 code. Okay, that CPU has to execute. Now suppose CPU executes this code, okay, this register 1 equals to count, that is this first one, the blue color, register 1 equals to count. CPU has executed. Now whatever was there in the count, that will be initialized in the register 1. Okay, so 5 will be initialized in the register 1. So 5 will be initialized in the register 1. Now after that, CPU has executed second code of the same program. Okay, now that is register 1 equals to register 1 equals to register 1 plus 1. So register 1 equals to register 1 plus 1. Now in the register, what is there? This is the current scenario. Okay, so in the register 1, what is there? 5 is there. Now 5 will be updated by value 1 and will be replaced to register 1. Fine. 6. Now the current value of register 1 is 6. It has been updated from 5 to 6. Okay, now after executing the second statement, the another code is executed from another subroutine, right, or another program. So for example, this code is being executed. Now you can now understand that after executing this first two statement, the register 1 have the value 6, but in the memory the count value is still 5, because the third statement has not been executed, and this count is the memory location that is shared by this both program. So this is blue color is from another first program and red color is from another program. Okay. So now after executing these two, now at time t equals to 2, CPU has executed register 2 equals to count. So this is the code belonging to another program. So register 2 equals to count. So now it has taken another register. CPU has taken another register, not the register 1. So, and register 1 and register 2 are not shared, only the count memory location is shared. So register count at this point of time, the count value is same, because this third statement has not been executed. So that's why in register 2 value 5 will be loaded. So basically register 2 contain value 5 at timestamp t2. Okay, now at timestamp t3, register 2, this register 2 equals to register 2 minus 1 will be executed. So when this statement gets executed, register 2 will be loaded with or stored with value 4. Now at the end, not at the end, after this statement, say for example at time t4, so at time t4 this code is executed, count equals to register 1. So what is happening out here? So if the register, whatever was there in the register 1, that is 6, will be loaded into the memory location, that is 6. And now again after that, this last statement of another program number 2 is executed, that is register 2 value is loaded into the count same memory location. So now the problem out here is in the execution of t4 and t3. So the final value of counter totally depends on sequence in which t4 and t5 is executed, right? T4 and t5 is executed. So it is basically creating a problem that in the memory the values 4 should be there or 6 should be there whenever CPU executes C++ or C minus minus. Okay, so this is the problem. The problem is in the memory 6 should be there or 4 should be there whenever computer executes count minus minus or count plus plus. But in turn, the actual implementation of count plus plus and count minus minus in machine level language form is 3 lines of code. Okay, so this creates a problem known as a data inconsistency problem. So this is the problem, and we all need to understand this problem. Data inconsistency is really a big problem, and it should not have happened. Okay, and whenever we write a program dealing with the cooperating process, and there are some shared memory locations or shared variable locations, then in that scenario data inconsistency problem may arise, and we should be very very cautious that whenever the process 1 is executing count plus plus, you should not allow the process 2 to execute count minus minus, as it leads to data inconsistency problem as shown out here. So in this example as shown out here, you will feel that okay, when this statement gets executed, you will feel that you should get answer as 6, but during the execution, okay, it may lead to 4 also. because here the computer will execute instruction, machine level instruction, not count minus minus. After compilation of your code, their code will become, this C++ will become 3 lines of code, and C minus minus will become another 3 lines of code, and these 3 lines of code will be executed in interleaved fashion. So this is the problem, and name of the problem is data inconsistency problem. So now we'll move to the race condition. Before I talk about the race condition, I'd like to give you the example about the race condition. So say for example, there is a class. Okay, suppose there is a class. Suppose there is a class, and inside the class, and this is a door of the class. Okay, suppose this is a door of the class. I am very bad in drawing, please bear with me. This is a door of the class, and lot of students are waiting. Lot of students are waiting in a queue, and the door is closed. Okay, and these are my like tables. Okay, chairs. These are the chairs orientation of the class. Okay, these are my chairs or tables, okay, where students will sit down for doing the exam or for appearing for the class. And if and the number of chairs inside the classroom is much less than the number of students who are waiting outside the class. Okay, so now, and the door is closed. Having said this situation, and one more assumption is that the students are from very or are of very junior, okay, maybe a LKG or UKG, where they rush whenever door is opened after the class or before it. They always try to run and try to grab the first seat itself. So suppose this is the scenario, that door is closed and there are limited number of chairs and there are huge number of students, very low less SD student, maybe a KG student. Now teacher has suddenly opened the door, and everybody try to rush and try to grab the seats. Now it might happen that whenever the student or whenever the student try to grab the seat, some other may also have grabbed the same seat. So this situation is known as a race condition. So this is just the example. The actual definition is something similar to this: a situation when several processes access and manipulate same data concurrently. So in our example, the chair was being accessed by more than one student because due to rush. Okay, so same thing might happen with the program where there is some memory location which is being shared by several number of processes. So those processes are trying to access and manipulate or update the data parallelly or concurrently, and the outcome actually depends on the order in which the access takes place, like the one in our previous example. And this was the order. So in this example we can say that okay, the final value of count will be 4. It might happen that the programmer is expecting 6 but it got 4, so it will be surprise for the programmer. So this is a kind of a data inconsistency problem, and the situation is known as a race condition. Okay, so and outcome of the execution depends on particularly order in which the access takes place is called the race conditions. Okay, now this is the race condition. Now we need to avoid, being a programmer, we need to avoid this kind of situation. So how can we avoid? We can avoid by maintaining a situation that suppose there is a, I'll just delete it. Suppose there is a process P, okay, P1, and there is a process P2. For simplicity, I'm only taking two processes, okay, and there is a shared variable. Okay, there is a shared variable. P1 also can access it, P2 also access it. Okay, and there is a variable is x equals to 5. Okay, so x equals to 5. Now P1 also can access this memory location, and P2 also can access. That's why P1 and P2 are concurrent processes, cooperating process. Okay. Now you can avoid race condition by imposing some kind of the rules. Like for example, if the process P1 is trying to access this memory location, P2 should not be allowed to access this. And similarly, if P2 is trying to update this memory location P1 should not be allowed. So this is the one example scenario where I can impose such kind of rules to avoid a race condition situation. So there comes the need of synchronization. So now, just now I have said that whenever you are allowing P1, whenever you allow the P1 to access the shared memory, you are not allowing the P2 to access it. So this rules can be imposed by generating the algorithm, by creating new algorithm, where the process P1 is can access the if process P1 is trying to access shared memory, P2 is not being allowed. So this is basically known as a synchronization. Okay, you are trying to basically synchronize the activity of execution between these two processes. So it might happen with 3 process, 4 process, 5 process, and number of process. So basically this is the reason for studying this chapter, that is process synchronization. So I hope all of you have understood the importance of risk synchronization for solving the situation of race condition in which the problem of data inconsistency arises, right? So now we'll move to the problem, critical section problem. So basically the main task, the main problem I've already described it, but the formal definition I'd like to describe it. So name of the problem, that whatever that I've talked about, the race condition, race condition situation, that is defined using the critical section problem with respect to programming, okay, with respect to process, okay, codes. Now let's try to define the problem. Suppose there is a system, okay, suppose there is a system, and in the system is computer system. In the system, or in the RAM, there are a lot of process. In the RAM there are a lot of process, P1, P2, P3, Pn. So there are n number of process. Okay, so those n number of process are there in the computer memory and shared, and those processes are cooperating process. So in short, they share, all those n number of process share some memory locations. Okay, so having said that, all those processes are there in the RAM and share some common memory location. Let me give you a diagrammatic view of the same. Suppose this is your RAM, okay, sorry, suppose this is your RAM, and there are a lot of partition in which in separate partition separate number of processes are there. So P1, P2, Pn, okay, and this Pn, and there is one common memory, okay, which is being shared by all of them, okay. So this, having said this, that consider a system and process. Each process has a segment of code and critical segment of code called the critical section, in which the process might change from common variable. I mean to say that there is a code with each one of them, P1, P2. Say for example, count plus kind of thing, or C++ kind of thing, and this is memory C. Okay, so P1 may manipulate this memory, P2 may manipulate this. So how does it manipulate? By executing code like C++ or C-, as shown in our previous example. Okay, so this code, updating code for manipulating the shared variable, is known as a critical section. So critical section is a section which is a code that will manipulate the shared memory location. Okay, so in short, that is in short. So there are various what kind of updation. Maybe it is trying to update the variable, or update the table, or writing a file, etc. so on. So this is all about the critical section. So critical section is a special kind of code which tries to manipulate the shared memory. Okay. Now this execution of critical section by the process is mutually exclusive in time. Means that whenever P1 is executing the critical section, maybe C++ or C-, whenever P0 is executing C++ or C-, no other process from this list, P1 to Pn, should be allowed to execute its critical section. This is known as a mutual exclusive. Mutual exclusive means P0, when somebody is executing the critical section, remaining processes are not being allowed. Okay. Now the problem is the problem, and now we are trying to define the problem. Now the problem is how to solve this problem. How can I allow some of the list, how can I allow one process out of list of process to allow execute and avoid or not to allow the remaining process to enter or execute the critical section. So this regulations, protocol means rules, okay, these regulations, defining these regulations or algorithm, okay, designing the protocol or algorithm is the problem, and the name of the problem is critical section problem. So I have to, in short, in order to avoid a race condition or data inconsistency problem, we are trying to basically design a protocol or the algorithm to avoid race condition. So how can we do so? Okay, so that is all about the critical section problem. Okay, now the basic outline I would like to tell you. Whenever, okay, say for example there are 5 processes, okay, say for example, suppose there are 5 processes, or in short there are 3 processes, P1, P2 and P3, and the shared memory by this is this, okay. So they try to manipulate the content of this memory location by executing the instructions like P1 might be executing C++, P2 might be executing C minus minus, P3 might be executing C plus 2, like that way, okay. So there may be n number of critical section code. So now whenever P1 is trying to, whenever P1 want to update this memory location, okay, whenever P1 want to update this location, maybe like P1 code is whenever P want to execute C++, okay, the critical section code is something similar to this, okay. So for this is C plus equals to 2. So in short, P1 is trying to update the memory by 1, P2 is trying to decrement the memory by 1, and P3 is trying to update the memory by 2, okay. So these are the critical section code. Now whenever P1 is trying to execute this, it has to satisfy certain criteria. It has to satisfy certain criteria. Now if this criteria is satisfied, then only P1 is allowed to execute C++. Now when P1 is executing C++, we should design a protocol in such a way that P2 and P3 is not being allowed, should not be allowed. So in short, whenever P1 wants to execute C++, it has to satisfy certain criteria, okay. This criteria is known as a entry section. This criteria is known as an entry section. So after satisfying the criteria for entry section, then only P1 will be allowed to execute C++. Now during the execution of C++, P2 and P3 should not be allowed to execute this C++ or C++ equals 2. Okay. Now this may be applicable to P2 and P3 same. Okay. So this is all about the entry section. So each process must request, so whenever entry section, okay, every solution to the critical section problem has an entry section and has an exit section. So to just like the entry, to come out of the critical section also, it has to satisfy certain criteria, that is known as a exit section. So basically entry section contains a piece of code, okay, and that piece of code tries to take a decision that whether the respective requesting process is allowed to enter the critical section or not. Similarly, that follows for the exit section. So apart from this code, apart from this C++, this type of code which update the common memory, there might be some other code with P1, P2, P3 respectively. So that code is known as a remainder section. Okay. Now, so in short, critical section problem is to remove the race condition situation or data inconsistency problem. So the problem is to design a protocol or the algorithm where I can execute the cooperating process that share a common variable without any problem, without any data inconsistency problem. Now whenever and now coming to the point, critical section is a piece of code. Critical section is a piece of code which will try to update the common memory locations shared by these different processes. Now, whenever such kind of code has to be executed, it has to satisfy certain criteria known as a entry section. Whenever it is coming out of such kind of processes, codes, it is known. It has to satisfy certain criteria known as a exit section. Apart from this critical section code, there are other codes with the process. Those codes are known as remainder section. Okay. Now, this is the general structure for one process pi. Okay, so in a system there may be n numbers p1 p2 p3 dot dot dot. So one process, this is the general structure. So whenever this is a critical section location, so in this it might happen that c++ or count minus minus, anything, it could be any code that will, here you will write down the code that will manipulate the common memory. Okay. And remainder section I have already told you. So in order to execute this code, it has to satisfy certain criteria, okay, known as the entry section. And entry section means it contains some instruction of the code which will try to qualify this process pi for executing critical section. Okay. This is all about it. Next is the example with respect to process two process. Okay, suppose there are two process pi and pj in the system. Process pi, say for example, is trying to execute critical section, then process pj should not be executing. It may happen that pj is interested, but since pi is executing cs, so the request for pj for entering the critical section will be not granted. Okay, or entry section qualified, it will not be qualifying the entry section criteria. So if pj is executing critical section, then pi will be somewhere in the entry section, and the qualification is not being made by the pi because pj is executing cs. Okay, so we most of the time use the word cs also for critical section. Okay. So this is all about the problem. Now we'll talk about the solution. Any solution that you are trying to frame, it has got three things. Okay, three criteria it has to always satisfy. So whenever you are trying to design an algorithm for solving the solution to the CS problem, three criteria it has to be satisfied. First criteria is mutual exclusion. Mutual exclusion means whenever a process pi is executing the critical section, no other in the list who are interested to execute the critical section should not be allowed. That is known as a mutual exclusion. Now next come to the point progress. Okay, so whenever you are designing a solution, mutual exclusion has to be avoided. Okay, mutual exclusion criteria has to be satisfied. Okay, now coming to the point progress. So I'll just read out the progress, then I'll try to explain with the example. If no process is executing in CS, then there exists some process who wish to enter the CS, then the selection of the process that will enter the critical section cannot be postponed independently. Okay, for example, suppose P1, P2, P3, all of them are interested, and none of them are executing critical section. Now all of them are interested, but none of them are executing the critical section. Then we should not postpone for decision making to select from the list of process who are interested to execute the critical section and who qualifies the entry section, and this decision cannot be postponed indefinitely. So decision has to be made within a finite amount of time whenever there is some process in the list who wish to enter the critical section, right? So this is known as a progress. Now next is the bounded waiting. Now bounded waiting, I'd like to take in the example. Suppose there is a process P1, this process P1 who wish to enter the critical section. Okay, suppose this is a process P1 who wish to enter the critical section and has requested for entry section validation. Okay, at time equals to 0. So P0 at time t equals to 0, P1 have requested, but since this CS was being executed by some other higher priority process, so P1 was not granted. So P1 has to wait. Now it might happen that at time t equals to 1, okay, at time t equals to 1, another process is given granted. P1 is not given granted, P1 is still interested, like that way. Okay, it might go on. At time t equals to 1, and the process is given granted. So what is happening out there is that P1 is waiting for indefinite amount of time. So this waiting should be some bounded or limited. So this is all. This is known as a bounded waiting. I'll just read it out. The bound must exist a number of times that other processes are allowed to enter the CS after the process has made the request to enter the CS before the request is granted. So you cannot allow the P1 to wait for indefinite amount of time once it has made the request for entering the CS, right? So you are allowing all higher priority process to execute the CS and not allow or asking the P1 to wait for indefinite amount of time. So this should not happen. So bounded waiting means you are trying to limit the number of waiting time for requesting process who wish to execute the critical section. So this is all about the critical solution to the critical section problem. Any solution that you are framing has to satisfy these three criteria: mutual exclusion, progress, and bounded waiting, right? So that's all for today's session. If there's any questions, please post it, or you can bring it up in our next session. Thank you so much.